Yeah, so I really appreciate this opportunity to speak in this session in memory and celebration of Phil. He was a friend for many years, and thinking about him, three things immediately came to mind. Firstly, he had a great enthusiasm for mathematics and the light that it could shed, and a great enthusiasm for communicating it to others, hence the book with Jim Lambeck and in his many writings and lectures. The second thing is laughter. Every conversation with Phil was punctuated with laughter. He loved the human foibles, which prevent us taking ourselves too seriously. But his laughter, the humor was always gentle and kind, which brings me to the third thing, his kindness. He was very kind to students and young researchers and to everyone that he encountered. So these are things I wanted to recall. Our interests overlapped in many areas, and we had many discussions, but we wrote one paper together. This is a paper on geometry of interaction and linear combinatory algebras, written with Phil and also Esfandiar Hagverdi, Esfan, who was then Phil's PhD student. And the work on that was done in the late 1990s. And that's what I want to talk about today. So geometry of interaction may be something of a blast for the past from many people. Let me recall that the term was introduced by Girard in a series of papers starting in the late 80s. The first preprint I mentioned there actually has the seed of the idea, but only for the multiplicatives. The important one for me is the geometry of interaction 1, where the main points of the construction are laid out. They're laid out, but they're not very easy to understand. If you want to try and read it, then I'd be interested if you do find it easy. And then there was work by Girard's students, Danos, Renier, and also Pasquale Malacaria. And I was trying very hard to understand what this stuff was. It looked interesting, but incomprehensible. And I eventually, as sometimes happens, the way I finally understood it was by kind of redoing it myself. But then it turned out different. And it was another example of the same thing. But what was the thing? So that was, this first thing was in work with Radha Jagadisan, who just joined me as a postdoc at Imperial College at the time. And it led to this paper on new foundations for the geometry of interaction, which was based, quite unlike Girard, who was using operator algebras on domain theory and fixed points, traditional tools from denotational semantics. Then in the work that I did with Radha, which Rick actually just mentioned, on games of full completeness for multiplicative linear logic, in the course of doing that, we realized what the original construction of Girard actually was. And it was now became clear to us. But what was it all about anyway? I mean, there's not very much geometry, I would say, in the geometry of interaction. There's certainly a lot of interaction. And there are actually, it's another one of those elephants where different people and different groups have different views of what it's about. So in the work of Danos and Renier, and as Girard's students working on this, leads to a novel kind of abstract machine. I should mention also my then student at Imperial, Ian Mackey, who also did early work on abstract machine structures based on ideas from geometry of interaction. And Danos and Renier found very nice connections with optimal reduction in the lambda calculus. Girard's own view was that geometry of interaction was interpolating between proof theory, which has dynamics of cut elimination. You can rewrite proofs to eliminate cuts. And on the other hand, static semantics, denotational semantics, in fact, coherent spaces in particular for linear logic. It's worth remembering that linear logic itself was found by reverse engineering from coherent spaces, which were a simplification of an earlier model that he'd given for system F. And once you simplified it in this way, then he could see that various connectives became meaningful, and you got in particular this full involutive duality. So the idea was that you could have this mathematical semantics which would be able to capture the dynamics of cut elimination without being based on syntax. Then there was the other thing he was keen to put forward in those original papers about the connection with operator algebras, which I found to be a complete red herring. And actually, interestingly, the paper by Renier and Malacaria, which I mentioned here, although it's got operator algebras in the title, actually made it clear, to me at least, that it had nothing to do with operator algebras, and all the relevant structure was carried by the category of sets and partial injective functions. And the way I was looking at it is a kind of adaptation of Girard's view to the setting of semantics of computation. So traditionally, we have operational semantics, which is syntax-based, and denotational semantics. And this was a novel way of interpolating between them, where you had a process structure and a dynamics. And in fact, it has a close connection, in my view. Well, it became clear to us with game semantics. This was just being developed at that time. That was when game semantics of programming languages of computation was being developed. And in fact, the view that I take is that we can more or less describe geometry of interaction as game semantics without games. What that means is the games are kind of types which constrain what the behaviors can do, but there's an underlying notion of the strategies that just operate without constraints and can interact with each other. And you can actually see the game semantics as imposing this extra type structure of games on this underlying very simple kinds of strategies. And this was how we, history-free strategies, in fact, which is how we came to see the connection in the work with Rada on this game semantics for multiplicative linear logic. Okay, now the thing that I understood, that got me into the geometry of interaction is essentially in this picture. Which eventually dawned on me, which really tells the story, at least at the multiplicative level. It's all there in principle. So we think you're in some monoidal category, if you like. So you have, so a process is if you a 2-input, 2-output box. So you can think of it as a morphism, say F from A plus tensor B minus to A minus tensor B plus. G is another such process, and you connect them by putting them side by side and feeding the second input of F into the first, the second output of F into the first input of G, and symmetrically with G, first output of G going to second input of F. And if you think of this dynamically, you think of some information. So what you end up with is, again, a 2-input, 2-output box. So you think of information flowing in, say, to F. F may immediately emit something to the environment on its first output, or it may send some information on its second output. And that then gets input into G, which can then react, and it may then produce something on its first output, and this way you can ping pong between F and G. If you're familiar with game semantics, you can see that this is exactly the kind of interaction between strategies that happens there. And eventually, after some long process of interaction, you may see an output coming from F or on A minus, or from G on C plus. So the question is, how do you realize this intuitive picture mathematically? The original way was to think, well, I know how to do feedback because we have recursion and fixed points, which we know how to interpret in denotational semantics. But there's also another way where you think of all this as a sort of, where you think of a monoidal structure as coproduct, and then a particle is entering in, traveling around the loop, and eventually coming out. And that is essentially the version that was appearing in Girard's constructions. One of the remarkable things about this is that this composition is almost commutative. It's commutative up to the symmetry of the monoidal product. And the fact that it's going to give you a dual situation is kind of immediate from this. You can flip things around across the monoidal symmetry. Now, what is the structure that lets you do this? Well, the answer, which was to come a little bit later in its proper generality, was that of traced monoidal categories. So a traced monoidal category has this, as well as in a symmetric monoidal category, say you have a trace which, if you have an A tensor B and a C tensor B, you can kill one input and one output. It's very important that, and so you get this feedback picture that we see here. It's very important to notice that this is a linear operation. We can see we match dropping an input and dropping an output. It's very much like the trace used in the tensor calculus in physics, where you kill a lower index and an upper index. And this is an important difference from similar looking notions that have been around in the computer science literature. For example, the iterative algebraic theories of Elgot, Bloom, and Eschik, which axiomatized flowchart iteration and which implicitly had copying in them. So you see you're splitting the output in this iteration, using some of it to go to the output and some of it feeding back into the flowchart. That's not a linear operation, but the trace is. So the mathematical essence, at least for the multiplicative GOI, is that you have feedback in a linear monoidal setting, and you use this to build a free compact closed category from a traced category. The remarkable thing about that is that on the face of it, a compact closed category is a higher order thing. You have all these function types, you have a closed category, but you're interpreting it in terms of essentially first order ideas. Everything in the picture that we drew, these pictures, is very first order. It's just boxes and feedback loops, sort of thing you could build with a circuit of some kind. So we're explaining at least linear higher order behavior in terms of a first order model, which again suggests that it's something to do with giving a process understanding of higher order computation. And the composition in this free compact closed category, in other words, the symmetric feedback I was just showing you, subsumes what Girard called the execution formula, and hence the dynamics of cut elimination. So the right answer to the question, what are these examples of, is the notion of trace monoidal categories introduced by Joyal, Street, and Verity in 1996. They were actually answering a different, I mean, their motivation really came from tangle categories and not theory, and they were working in a braided setting, but taking it down to symmetric monoidal categories is gave exactly the right answer for the examples that we built, as it were, avant la lettre, and actually showed these examples to Andre in Montreal at some point. So trace monoidal categories gave us the answer. Well, let me just give a feeling for what the kinds of things trace monoidal categories can be. I would say there are three natural families that arise, and which characterize most of the pretty much all the examples that have been considered to date. There's the ones based on coproduct or disjoint union, and typical examples would be the category of sets and relations, of partial functions, of partial injective functions. As soon as you go to infinite sets, then putting things going around feedback loops is in general going to enforce partiality. Partial functions and partial injections are the things to think of there, and also things like matrices over a Kleene algebra. So I dubbed this particle style because if you think about it dynamically, if you think of those boxes, for example, here, then if you think of this as a disjoint, oops, I'm going the wrong way. If you think of this as if you think of this in terms of the monoidal structure being coproduct, then you're really saying an input will come either on A plus or on C minus, and it will sort of, the resulting outputs will wander around. There'll be a unique track, as it were, of a particle flowing around the system. I don't think that's too fanciful, although I remember the reviewers of our paper got a bit annoyed with us or with me for, there's a lot of retracing in this. presentation, my apologies, because I then, I sort of said, well, let's call the one based on the product wave star, why not? So particles and waves. So they said, really? Do you mean particles and waves? Well, I mean, this is what I mean. And in fact, Hasegawa and Hyland showed that if you take the trace monoidal category axioms where the tensor product is a categorical product, then it has to be a fixed point operator. And necessarily then we're essentially in the realm of domain theory. And this was exactly what the new foundations example gave. And by the way, this led on to the notion of concurrent games, which I introduced with Paul-André Méliès in '99. And now there's, of course, a big activity on the more general notion of concurrent games by Glyn Winskill, Pierre Clérambault, and their co-authors. The third kind I would mention, I mean, both of these are causal in there's a flow, whether it's a single particle traveling around a system or whether it's information globally in a product, so a wave of information flowing through the system and increasing according to some fixed point iterations. Whereas the final examples are things that are compact closed categories to start off with, like the category of relations or finite dimensional vector spaces. And those are acausal, but they're still traced. You can always, given a compact closed category, extract a trace from it. And this was also, incidentally, led to my first paper with Bob, who I think is here, was on physical traces and was the sort of first step on the path towards categorical quantum mechanics. Okay, and in a paper on retracing some paths in process algebra, I kind of laid out how this multiplicative part of geometry of interaction could be understood in terms of traced monoidal categories, and this construction of the free compact closed category, essentially the int construction of Joyal Street and Verity. Incidentally, the reason for the name int is that you can take as a simple prototypical example turning the ordered monoid of natural numbers into the ordered monoid of integers by taking differences, pairs of natural numbers as differences. And the trace is the cancellation property for the ordered monoid. If m plus p is less than or equal to n plus p, then m is less than or equal to n. That's exactly what it is. Okay, so, but this wasn't the whole story of GOI. It's important to say that, because GOI was covering at least the multiplicative exponential fragment of linear logic. And in particular, it could cover the lambda calculus, and it was computationally universal if you took a type-free version. So one wanted an axiomatic framework to cover the whole of GOI and to be able to achieve computational universality. The other thing, which was noted right from the beginning, is that GOI does not give an honest or standard categorical model of linear logic or of lambda calculus. Many of the natural equalities to do with substitution fail. So for example, in lambda calculus terms, it doesn't give you a lambda algebra, let alone a lambda model. And many of the kind of commutative conversion type equalities that you would have in the proof theory of linear logic don't hold. So a reasonable question is, if it isn't doing that, what is it doing? Can one calibrate that with some reasonable positive notion? So I kind of suggested an approach to answering these questions. Phil and Esfan was doing his PhD with Phil, got interested, and this developed into the joint project and led to our paper and the happy circumstance of writing a paper with Phil. So, I mean, what are our answers? So we introduced GOI situations, not a very lovely term, but as an axiomatic framework for the full GOI construction, including exponentials. And our proposal for what it is, if it's not a standard model of linear logic or the lambda calculus, is to take combinatory algebra as the right level. And we introduced in particular linear combinatory algebras and showed that these gave rise to standard computationally universal computational algebra. And then the main result of the paper is that every GOI situation, every axiomatic situation gives rise to a linear combinatory algebra. Now, combinatory algebras maybe in this crowd haven't had such a good press, but they're not so bad. Let me give you a few things. I mean, conceptually, they're algebras of closed terms. Essentially, if you give combinators enough arguments, they do the right things. If you don't give them enough arguments, they won't satisfy all the equations, you know, you would hope to have in a fully in a sort of properly extensional system. So the basic axioms, which are the only ones I'm interested in here, are weaker than those of lambda beta. They don't form lambda algebras. On the other hand, there's this minor miracle that the equations of basic combinatory algebra are just good enough to show that all partial recursive functions can be represented, acting on numerals, of course, encoded as the combinator equivalent of Church numerals or whatever. So it is a universal, it's a succinct, purely equational presentation of computability, and quite, I think, quite beautiful in those terms. And there is a Curry correspondence. Incidentally, there's the Curry-Howard correspondence. Curry's part of it was for combinators, because Curry was Mr. Combinators. We'll recall that in a moment. And of course, combinatory algebras form the basis of realizability, which is exactly a machine for turning intentional models of computation, such as combinatory algebras, into extensional models, even toposes. And they're very handy for substructural logics. If you have I mean, they correspond to Hilbert-style proof systems, and you can always drop a few axioms or, vary the axioms a bit. So things like BCI and BCK algebras have been studied for a long time. And from our point of view, they capture exactly the right level of intentionality for geometry of interaction, explaining why it suffices for computation. So in fact, everyone knows, I hope, the SK combinators of Schoenfinkel, but Curry's original set of combinators was B, C, K, and W. You know what K is, and here's B for bracketing, C for commuting the arguments, and W for doubling. And if you take their principal types, which you can compute from the Hindley-Milner algorithm, then you see that they really, this makes sense of them logically. This is Hilbert-style axioms for pure implicational logic. And you see that K stands for weakening and W stands for contraction. And C is for exchange. And the B combinator is really the unary version of cut. So actually, Curry's combinators corresponded to the Gensen structural rules, and the Gensen set up for sequent calculus, but done in this algebraic style in combinatory algebras. So then the sort of idea was to introduce a notion of linear combinatory algebras, which would be to linear logic, or at least its Bang linear implication fragment, which is the bit that's relevant for us, as the usual ones are to the purely implicational fragment. So as well as an application, we introduce a unary operator, which would just correspond to the necessitation rule in Hilbert-style presentation of modal logic. And you need a bunch of combinators, B, C, I, and K. And well, BCI is as we would expect. And this is the application is actually linear application. And now for the K for weakening and W for contraction, we need to have a banged argument. This is the point. So this is expressing the usual idea in linear logic that you can do weakening and contraction, but only for banged formulas in a suitable context. And then you get dereliction, co-multiplication, and monoidal functoriality. And again, we can give the principal types, which make it clear that this is a Hilbert-style presentation, or this is witnesses, proof witnesses for a Hilbert-style presentation of the linear implication Bang fragment of linear logic. And you can then do a combinatory version of the Girard translation, and what you get is that given a linear combinatory algebra, we can construct by interpretation a standard combinatory algebra out of it. So if you have one of these linear combinatory algebras, you do have a universal model of computation. Okay, so now what's a GOI situation? So it's going to be a trace symmetric monoidal category. That's going to take care of the multiplicative part. And now we introduce an endofunctor with some things that look to have the right kind of shape to be able to handle co-multiplication, dereliction, particularly contraction and weakening, the copying and discarding of things that you need with respect to the bang. So, but these are only given as retractions. Using retractions rather than isomorphisms is, of course, an old trick in models of the lambda calculus. So it's the way you turn P omega into a model of the lambda calculus, and it's not fully extensional and so on. And we can apply the geometry of interaction construction to the trace monoidal category to get a compact closed category. That's taking care of the multiplicatives. And then we can define the exponential bang on this compact closed category using the functor T. Okay, because the monoidal structure holds only up to retractions, we get only a weak linear category in which the naturality requirements are weakened to pointwise naturality. And this is exactly matching the idea in combinatory logic that lambda equations hold only for closed terms. This matches what geometry of interaction actually does. And then we can complete the construction. We start with this GOI situation. We build a weak linear category. We extract a linear combinatory algebra from it. To get the untyped version, we assume a reflexive object, which is itself closed with retractions under the monoidal product and the T functor and so on. But you can also get a typed version. And then we, as already explained, we get a combinatory algebra from that. So I do want to show a few, I'm not going to show any formulas, but I'm going to show some pictures. This is what functional application looks like. It's a special case of the symmetric feedback that we showed earlier. So G is the function, and it gets called from the environment on the free input, and it may need to interrogate its input, so it sends something to the input of F, and this gets fed, and the F's answer gets fed back to G. Maybe you go a lot of times around that loop, and eventually, hopefully, whoops, G responds to the original question. And the I combinator, you see, is just a copycat strategy, or in fact, it's just the monoidal, it's just the symmetry of the monoidal structure. This is the yanking axiom of trace monoidal categories, in fact. And quite nice is the B combinator that we saw earlier. Remember, B of X, Y, Z, all bracketed to the left, turns into X applied to Y applied to Z. So it's a higher order operation that's re-bracketing the function applications. But actually, to achieve it in this model, all we need to do is put three copycats together, three twist maps together. And if you follow the information paths around these feedback loops, you see that an input request will go to X, the sort of the top function. It has to provide the answer. If that needs an answer from its input, it gets fed back to the input from Y, sorry, the output from Y. And sorry, to an input from Y, calling on Y to give its answer, similarly for Y to Z, and then the answers from Z get fed back to Y, and the answers from Y get fed back to X. So you can sort of see at the level of the information flow that this has exactly the required behavior. The W combinator is really just an infinite combination of copycats where we sort of relate to, I mean, if this is the Hilbert Hotel business, that if you take, just take n product, your underlying set, that's what the functor is doing in this concrete case. So you're turning two copies of n cross x into one copy of n cross x using an isomorphism between n, the natural numbers, I mean n, and n plus n. So it's just a kind of translation between dialects, but it's just being done at the simple level of copying information. So just to finish up, Phil and Esfan, I mean, this became, I think, the main focus of Phil's research for a decade. And Phil and Esfan wrote a further series of papers on topics including type geometry of interaction, unique decomposition categories, and partial traces. And they wrote a nice tutorial on their work in the New Structures in Physics volume edited by Bob. And lots of nice work that's been done. If you want to see a very simple and concrete version of these ideas, I wrote something about how it gives a basis for a structural approach to reversible computation in terms of a very simple notion of reversible automaton, which in the end shows that you can build a combinatory algebra from remarkably simple material, namely partial involutions, graph matchings. So graphs in which each vertex has at most one edge incident to it, simplest possible kind of graph. Okay, so I think I'll stop there. Thank you.
I was wondering if you could say more about this memory pool extension of GoI, and if it relates to the feedback categories that we talked about earlier this morning, where they generalize trace categories where you do not have yanking anymore. Is that the sort of categories you would?
I'm not the, well, so this was work done by Hoshino, Asuo, and Moroka. So I'm not the best person to answer that. But essentially, you're sort of, they're adding, what they're doing is adding effects to this setting. I mean, in the original examples we discussed already showed you could have stochastics and other things. I mean, they added also quantum at some point in another work. So it's really adding effects to the monad and building a trace monoidal category out of that. I'm afraid I've been at I think I was in the other track, so I didn't hear your talk, so I can't comment on that. But I mean, there may well be a connection there. Okay.
We're going to carry on to the next one in the interest of not annoying the physicists who wish us to leave at 5:30.